We're going to be solving Cambridge International AS and A Level Chemistry, Paper 2 AS Level Structured Questions, October-November 2025, Paper 22. Manganese, Mn, and its compounds are widely used in many chemical reactions. Okay, so we have Mn. Mn is usually found as a single isotope, which is manganese 55. Determine the number of protons, neutrons, and electrons in an atom of manganese 55. So the number of protons is going to be determined from the periodic table. We got to go to the periodic table and check the number of So where is Mn55? 55 we're looking for, and we're looking for Mn. So we got to find it in the periodic table. So where is Mn? This is Mn. So over here it's written 25. So 25 is going to be the proton number. If someone tries to think that they should take mass number as 54.9, it's going to be considered wrong, because the examiner clearly tells you that he needs the neutron number for manganese 55. That means it should have 55 nucleons, right? So 25 is the number of protons, and 25 is going to be the number of your electrons, because we're dealing with an atom, and neutron is going to be 55 minus 25, right? So you gotta be careful with such kind of stuff. So it's 55 minus 25, which gives you 30. So you're gonna have 30 neutrons. Define isotopes. Okay, isotopes are atoms of the same element with the same number of, so we're gonna write the full definition. Atoms of same element, the element is the same, with same proton number, but different neutron number, So the neutron number is different, right? But the proton number is the same. A sample of Mn manganese from the moon is found to contain manganese 53 in addition to manganese 55. State two pieces of information needed to determine the relative atomic mass AR of manganese in this sample. So to calculate the relative atomic mass, you know what you need. Firstly, you need the mass of the two of your isotopes, and the second thing is that you need the relative abundances of the isotopes, right? So first thing is the mass number for both isotopes. That's the first information you need, and the second you need is the relative abundances of both isotope. Of all the isotopes of both isotopes that you have, right? The shorthand electronic configuration of manganese is AR 3d5 and 4s2. Complete the full electronic configuration of manganese. So they've written 3d5 and 4s2. This part has been written for you here. So what you gotta write is just this part, right? You gotta write it, the electronic configuration for AR. And you know for AR, it's 18 electrons that you gotta fill. So you're gonna say 1s2, 2s2, 2p6, 3s2, and 3p6. Do they make 18 electrons? 2 plus 2, 4, 4 plus 6, 10, 12, 12 plus 6, 18. Done. Reduce the total number of unpaired electrons in an atom of manganese. So you know that the 4s2 and 3d5. So 4s2 and 3d5. So I'm going to draw 4s2 at a higher energy level, something like this. And this is your 3d5. Right? So 3d5 means you have 5 electrons in it. 1, 2, 3, 4, and 5. And 4s2 means you have 2 electrons in your 4s orbital. So that's your 4s, and this is your 3d orbital. right? 3D orbitals. So you can see for yourself, we have to reduce the total number of unpaired electrons in an atom. The 4s electrons, they're paired. So there are only these 5 electrons, 1, 2, 3, 4, 5 electrons that basically lack a pair. They don't have a pair. So these 5 electrons are your unpaired electrons. This 4s electron is paired, and all these remaining electrons, they're also paired. You can draw the 1s 2 orbital. You're going to see both electrons are paired. So the only unpaired electrons are this, 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 and this. In the 3D orbitals, in the 5 orbitals of 3D, you have 5 unpaired electrons. So the answer is going to be 5, right? Manganese IV oxide reacts with methanol. This is your methanol, and in acidic conditions to produce carbon dioxide. The movement of electrons to or from relevant species is shown in the following half equations. This is your first equation, this is your second equation. So what's happening is that if you try to understand, over here you are losing 4 electrons, and over here you are gaining 2 electrons, right? So that's what's happening. Loss of electrons, which is going to be oxidation, and gain of electrons, which is going to be reduction. So the first equation simply represents oxidation, and the second equation represents your reduction process that's happening. Okay, identify the species that is reduced in the half equation to explain your answer. Okay, I said that reduction is happening, but which species is being reduced? You know, over here, if you look at Mn, if you try to reduce its charge in the first equation, since oxygen is a -2 and you have 2 oxygen, so -2 times 2 gives you a -4. So oxygen is a -4. To balance out this -4, you gotta have a +4. So Mn is a +4 over here, and over here Mn is a +2. So when you move from +4 to +2, basically a decrease in your oxidation number is happening. So this is your decrease in oxidation number. So identify the species that is being reduced. The species is simply MnO2 is being reduced. Why is it being reduced? We're gonna tell, because the oxidation number of Mn reduces from a +4 in MnO2 to a +2 in Mn2 plus. So there is a gain of 2 electrons. We're going to tell everything we know, which is reduction, right? Gain of electrons is called reduction, and Mn is the one that's being reduced because it's gaining electrons. The oxidation state of carbon in methanol is 0. Calculate the oxidation state of carbon in carbon dioxide. So they're telling that in methanol, carbon is a 0. Why is it a 0? Because look, hydrogen is going to be a +1, oxygen is going to be a -2, right? So to balance out this -2, you need a +2. That's why you have 2 hydrogens, right? In carbon dioxide, you have to calculate it out. You simply know CO2, right? Oxygen is a -2, and you have 2 oxygens. So -2 times 2 equals to -4. So oxygen in total gives an oxidation state of -4. To balance this out, you only have 1 atom, that is carbon. So carbon is going to be a +4. So you're going to write +4. Okay, construct the ionic equation for the reaction of manganese IV oxide with methanol in acidic conditions. So now we have to write an ionic equation. These are the 2 equations. We have to combine the 2 equations, and we have to cancel out the species that come twice or thrice, and we also have to do one else thing. We got to balance everything that's on the right and on the left, right? So what do? We cut everything that we don't need. So the first things first, we got to clean our area, right? We got to clean it, and then we got to realize what do we have to do. Okay, so now I'm gonna break the equations from their middle, this part and this part, right? This part is 1, this part is 1, and this entire part is 1, right? So now I have to check which things come on both sides. If I look at this side, I can see I have 4H plus, and over here I also have a 4H plus. They're both the same, so I'm gonna cut them. 4H plus cut with 4H plus, right? I can see 1 water on this side and 2 waters on this side. So this 1 water gets cut and this 2 gets cut, right? Now 1 water is left. Now what else do I see? I see 2 electrons on this side, 4 electrons on this side. These 2 electrons get cut and these 4 becomes 2 electrons, right? Because 2 electrons just got cut. So now what do I have left? I have 3 species left on this side. This thing on this side, carbon dioxide, Mn2 plus, and 2 electrons and 1 water on this side. That's exactly what I'm going to copy below now. Right? What I'm going to write is CH2O plus MnO2 is going to give me carbon dioxide plus Mn2 plus H2O plus 2 electrons, right? So that's going to be my ionic equation, right? What do you guys think? Is it correct? I think it is. Okay, next question states, the period 3 elements show trends in physical and chemical properties across the period. Explain why elements sodium to aluminum are good electrical conductors. Why are they good electrical conductors? Because they're metals. And you know, what do metals have? Metals have basically a positive cation thing and delocalized electrons. And these delocalized electrons can move through the metal to conduct electricity. So we're going to tell the examiner, why are sodium to aluminum good conductors? Because firstly, we're going to tell that they are metals, right? Metals which have a metallic lattice, right? Which contains a sea of delocalized electrons, that can move through the lattice to conduct electricity, right? Or you can tell the examiner that these are mobile electrons. Explain why elements P, S, and Cl do not conduct electricity. Because all their valence electrons, right, are involved in covalent bonding or involved in covalent bonding. So there are no free delocalized electrons. To conduct electricity. That's all. Figure 2.1 shows the variation in melting points of period 3 elements from silicon to chlorine. That's silicon, that's phosphorus, that's sulfur, and that's chlorine. So what's happening is the melting point is decreasing, then increasing, then decreasing. Why silicon has the highest? You should know that it is a giant covalent structure. So this is a giant covalent structure, and to melt it we gotta break the strong covalent bonds, and phosphorus, sulfur, and chlorine are your simple molecular structures, right? Simple molecular structures. Explain why there's a large difference between the melting point of silicon and the melting points of phosphorus, sulfur, and chlorine. We're gonna simply tell silicon is a giant covalent structure right? Giant covalent structure, and to melt it, strong covalent bonds needs to be broken, right? While phosphorus, sulfur, and chlorine are simple molecular structures with weak intermolecular forces of attraction, with weak intermolecular forces of attraction that needs to be overcome, right? That's all. The C part states, Table 2.1 gives some information about period 3 chlorides. Rho B refers to the pH of solution that forms when the chloride of period 3 is added to water. So what you have a chloride, right, which is going to be a period 3 chloride. So there's going to be a Cl in it, so it's going to be XCl. And then you're going to add water to it, and you're basically checking out the effects. So over here there's a table that you have to fill, and this table is for how many marks? 4 marks. And I believe that people say that in A levels don't buy books are a waste of money. Bro, this entire table, it came from the book, right? So I think books are damn important. In case you don't have notes or anything, books help you out, okay? Because they have the syllabus covered. So this is a table, exactly in the book. Oxidation number of the element bonded to chlorine. For sodium, it's going to be a +1. For magnesium, it's a +2. For aluminum, it's a +3. For silicon, it's a +4. And for phosphorus, it's a +5. I don't think it needs any explanation. pH of the solution when added to water, NaCl is gonna make a neutral solution. AlCl3 is gonna make a solution of pH 3. And in case you guys don't know that what I'm writing or what am I doing, guys, please open your books. It's a table in the book. You know that orange book which says Chemistry for Cambridge International AS and A-level course book by Laurie Ryan and Roger Norris? That's a very important book, okay? Buy that book, buy any other A-level books, buy any notes or whatever, and learn these things, okay? Because in chemistry, these are the things you gotta learn, rote learn, right? And then for SiCl4, it's gonna be 2. For PCl5, it's also gonna be 2. And for SCl2, which is sulfur chloride, it's also going to be 2. And that's all stated in your book. Bonding, in NaCl, it's going to be ionic. For ionic, we have to make an I. For covalent, we have to make a C. For metallic, we have to make an M, and that it goes on. MgCl2, it's going to be ionic. For AlCl3, it's going to be ionic, right? Okay. If they say it's ionic, then we gotta believe it's ionic. They've given it themselves. It's fine. SiCl4, it's definitely going to be simple molecular. So we're going to say simple covalent. But for structure, we're going to write simple, right? Over here, the bonding is only going to be covalent. Structure is going to be simple because two nonmetals covalently bonding to each other. Simple covalent. PCl5, definitely going to be firstly, it's going to be covalent, then it's going to be simple. This is going to be giant. This is going to be giant because they're giant ionic structures, right? Moving on. Write an equation for the formation of AlCl3 from its elements. So we have element aluminum. We have element that's chlorine. And then we're forming AlCl3. I guess the important part in this equation is not just writing the equation. You have to realize one thing, right? What's that one thing? That how do you balance this equation? Balancing is the main part over here. So over here comes a 2, over here comes a 3, and over here comes a 2. So gotta balance it out, otherwise you're not good to go. Write an equation for the formation of H3PO4 from PCl5. So you add PCl5 to water, which is H2O, and then you're going to form two products, right? You're going to form two products. These equations are what you have to learn. There's no shortcut, right? There's nothing that you can do. There's nothing that you can do if you don't learn them. So you got to just like learn them. You're going to form HCl, and then you form H3PO4. But there's one thing that balancing, it's fine that you don't learn the balancing, but you have to learn the products. So a 5 over here, and I think we're good to go. The next states that SCl2 reacts with Cl2 in a reversible reaction to form SCl2 liquid. Okay, so S2Cl2 is going to react with this chlorine. This thing going to react with this thing in a reversible reaction to form SCl2. Under certain conditions, a dynamic equilibrium is established. So you're forming a dynamic equilibrium, which means that the rate of your forward reaction equals to your rate of your reverse reaction. The concentration of your products and reactants remains unchanged. You got to learn these two things about equilibrium. So this forming this state, what is meant by dynamic equilibrium. Now whatever I just told you, you have to copy paste that thing. So I'm going to write it. Two statements. Rate of forward. The next part says identify the condition necessary to establish a dynamic equilibrium. That's a very important question. You guys should know that equilibrium cannot be established unless you have a closed system. So the only thing that you need for an equilibrium is that nothing should enter or leave the system. SCl2 is yellow and S2Cl2 is yellow and SCl2 is red. Okay, so what do we know? We know that this guy over here is yellow and it's all yellow, and this guy over here, it's red. State what is observed when the following changes are made to the equilibrium mixture of this and this. Explain your answers. The equilibrium mixture is warmed gently. So you know that it's an exothermic reaction, which means that the forward reaction is exothermic. If the forward reaction is exothermic, you definitely know that the backward reaction gotta be endothermic. And over here, you are warming the mixture. When you're warming the mixture, you're providing it heat. And when you're heating it, you gotta know that what's gonna happen is that you heat it. You provide heat to it. The equilibrium is gonna move backwards. Why? Because you're trying to increase the heat. The equilibrium is going to try to decrease it, and if it's going to try to decrease it, it's going to do the endothermic part, because endothermic part absorbs heat. So we're going to tell, observation is going to be that solution turns yellow, and it's all yellow. Why solution turns yellow? Gotta realize equilibrium is moving backwards, and when it's moving backwards, it's going to turn yellow. Solution turns yellow. Explanation: forward reaction is exothermic. Okay, that's simple. Forward reaction is exothermic and backward is endothermic. The overall pressure of the equilibrium mixture is increased. So now you're increasing the pressure of the equilibrium mixture. You know that when we're dealing with gases, pressure matters, but when we're dealing with liquids, pressure does not matter. So over here, pressure is only going to affect gas, not liquid. Over here, we have 1 mole of gas. Over here, we have 0 mole of gas. And the overall pressure of the equilibrium mixture is increased. When we increase the pressure, equilibrium moves towards the side. When we increase the pressure, equilibrium moves towards the side that has less number of moles. So we have increased the pressure. So equilibrium is going to move toward the side that is less moles. Those are 0 moles. So equilibrium is gonna move forward, right? Equilibrium is going to move forward. So we're going to tell when it's going to move forward, it's going to turn red, right? So observation is going to be that solution turns red. Why? Because you're gonna tell more gaseous moles on reactant side compared with product, compared with, or instead of reactant side, it's better if you tell them on the left side, because I've seen in marking schemes left side is more, acknowledged than the reactant side. Compared with right side, and then you tell the examiner that more gas is mold on the left side compared to the right side, and you tell that because since we're trying to we're trying to increase the pressure, equilibrium tries to decrease it. So we're gonna tell more, and volume and pressure are inversely proportional. More volume of gases on reactant side. That's why equilibrium is going to move forward, because it does not want gases, it want to decrease the gases. Okay, aqueous MgCl2 reacts with aqueous sodium carbonate to form a white precipitate. So over here we have a salt which is reacting with another salt to form a white precipitate, and that white precipitate is going to be of magnesium carbonate, because we know that sodium chloride is going to be a soluble salt. It's going to be a double displacement reaction. Upon heating, the white precipitate undergoes thermal decomposition, so our MgCO3 is going to thermally decompose to form what? To form MgO plus carbon dioxide. Construct an equation to show the reaction of MgCl2 and sodium carbonate. Use state symbols in the equation. So we have aqueous MgCl2, right? So what we're going to do, we have MgCl2, that's aqueous because it's soluble. Then we have sodium carbonate, Na2CO3, that's also going to be aqueous, right? For aqueous, don't write liquid over here, bro. It's not, molten. It's aqueous, so it's going to be AQ. And that's going to form MgCO3 plus NaCl, and there's going to be a 2 over here. NaCl is soluble, so it's going to be aqueous, but MgCl2 is going to be, magnesium carbonate is going to be a white precipitate. And identify the products of thermal decomposition. It's going to be magnesium carbonate, so magnesium carbonate and carbon dioxide, right? Form a carbonate. Oh, sorry, magnesium oxide and carbon dioxide. Sorry, because we're decomposing it. Magnesium oxide and carbon dioxide. Initially, we had magnesium carbonate, then we thermally decomposed it. So we formed an oxide and carbon dioxide. State the trend in thermal stability of group 2 carbonates down the group. It increases. Because you know that what's happening down the group is that it's difficult to decompose it because the reactivity increases. So over here you have magnesium, then calcium, then you continue to have more elements. What happens is that as you go down the group, strontium, barium, radium, what happens is that it gets more reactive, right? It gets more reactive, and when it's more reactive, it tends not to decompose because it can form ions more readily. It tries not to decompose. So we're going to tell the trend in thermal stability increases because a stronger bond is formed, right? The alkanes are a homologous series of organic molecules. Alkanes are generally unreactive and commonly used as fuels to define homologous series. So a group of organic compounds that have the same general formula, that differ by one methyl unit, that have the same functional group, that show a trend in physical properties, and that have the same chemical properties. That's all I know. And despite knowing a lot of stuff and having just 2 marks, I'm gonna write all the stuff. I'm not gonna give examiner a chance to detect any of my mark. Like, I don't know what's written in marking scheme. So me over here solving this paper, what is this paper? 22 October, November 2025. I'm gonna give him all the points, everything I know, because I don't know what's down there on the marking scheme, right? So let's go. Let's write a group of organic compounds with same functional group, hence similar chemical properties, because the functional group determines your chemical properties, hence similar chemical properties having a trend in physical properties, having a trend in physical properties, and each successive member differs by 1 methyl unit, right? That's what I know. Each successive member differs by 1 methyl unit. Having the same general formula as well, right? Or having same look, I am occupying a lot of space. I know that's not right, but I don't know. That's all I've learned in my GCSEs, that these are the things. Now I tell you what's there in the marking scheme out of all the things we wrote. A family of molecules with the same general formula. So they have this general formula thing, then they have the molecular formula differs by 1 methyl unit, 1 methyl unit. They have this thing, and then they have similar chemical properties or reactions. Similar chemical properties having a trend is not mentioned. So similar chemical properties. So if you mention this, and this point, you're going to get your 2 marks, right? But we mentioned other things as well, and I highly appreciate you guys mentioning everything you know. Everything you know about that's relevant, right? Not out of the blue. Give 2 reasons to explain the general unreactivity of alkenes. Firstly, we're going to write a sigma bond. 4 sigma bonds, like carbon has 4 sigma bonds. Yeah, there are strong CH bonds. And the other thing is the bonds are not polarized, right? Look, there is no electronegativity difference between carbon and hydrogen. So sigma bonds, which are strong CH bonds, difficult to break, and then they're non-polar. Why? Because when you have a carbon atom and you have 4 hydrogen atoms bonded to it, if it's polar and there's a large electronegativity difference between this and this species, this is going to be partial positive and this got to be partial negative, then this is going to pull the electrons towards itself, and this part is going to be reactive because this bond could break anytime, because this bond is unstable, because there's unequal division of electrons in it, right? But over here, the electronegativity difference between this and this species is so small that the bond tends to be non-polar, right? So electrons are like in the middle. They don't tend to be towards carbon or hydrogen. So you got to understand this thing. Alkanes with low relative molecular mass, or MR, are more useful than those found in heavier crude oil fractions. We know that when it has a low MR, the smaller alkanes, we use petrol or kerosene oil, so they're more useful than those that are like 30 carbon chains long. We don't use them that often. Name the process that's used to obtain alkanes with lower MR from heavier crude oil fraction. You just use the process that's called cracking. You crack the hydrocarbons, like the alkanes, the longer ones, into smaller ones. That's simple. Hexane, which is C6H14, has 4 structural isomers. Shows the hexane and 2 of its structural isomers. I gotta draw C and D, right? Complete figure 3.1 by drawing C and D. Okay, no problem for me. What the examiner has given me, I need to first realize that. He's given me a straight chain, like 6 carbons, like 1, 2, 3, 4, 5, and 6. And then over here in A body is given me like 1, 2, 3, 4, 1, 2, 3, 4, then a carbon here, and then a carbon here. Over here is given me like 1, 2, carbon here, 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 and then here, right? It's something like this, and I have to draw C. So I have to gotta look, what can I do? I can make a 4-member chain, like 1, 2, 3, 4. And on the second one, I can put both carbons. And then for the last one, what I can do, I can make a 4-member chain, 1, 2, 3, 4. Over here, I did it on the second, but if I do it on the third, it's going to mean the same. So I make a 3-member chain. What do? I put a C here, C2, H5 here, and a C here. Now, if that's my longest chain, that's 4. And out of the 4 on the second, I have both. That's the same thing. Can't draw this. Okay, I gotta think for it. What can I draw? 6 carbons. And in that 6, I gotta include a chain. So if I make it like 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 5 is just given it like on the second one. If I draw in the 5 on the third one, look over here. If I make it on the third one, that's a different thing. That's 3-methyl pentane, and that's 2-methyl pentane. So one thing I'm gonna draw is like 1. No, bro, you gotta draw it beautifully. So 1, 2, 3, 4, 5. 1, 2, 3, 4. This looks awful. I gotta make it like aesthetically. One, 2, 3, 4, 5. On the third carbon, I have a methyl chain, right? Over here, 1, 2, 3, 4. So 1, 2, 3, 4. On the second carbon, I gotta draw. Done. Okay, so that is what I knew. I suppose it's like to be that, but I don't know. So this and this. Done? Okay, so now I erase whatever I've done because examiner is going to be like, oh my god, I asked for the structural formula and you were writing the other one, right? A and B and hexane have different boiling points. Yeah, they're going to have because of their different chains, right? Arrange A, B, and hexane, A, B, and hexane in order of the increasing boiling point. So the highest is going to be of hexane, right? Why? Because the flat chains, they have the highest melting points. Why? Because when another hexane molecule is going to lie over here, it can lie close to it, right? And other hexane molecule can lie close to this hexane molecule. That means there are going to be more van der Waals forces between the two hexane molecules, right? After that, we're going to look at the branching. The more branching you do, the lower your melting point gets. So I'm going to write over here, more branching means lower melting point. So over here, I can see that I have a single branch. And over here, I can see that unfortunately, I have 1 and 2 branches. So I know that for a single branch, the melting point is going to be higher. For two branches, it's going to be lower. So then it's going to be A over here, and then it's going to be B. And the reason for that's going to be like unbranched has stronger IMFs because the molecules can lie closer together, right? For the more branched, it's going to be lower. And you have to also include a very important point. Whenever you're dealing with melting boiling points, you have to write this word, more energy required to overcome. That's very important. So first we tell them that unbranched molecule, hexane, means that in molecules can lie closer together, means that molecules can lie closer together, so stronger IMFs, intermolecular forces, or stronger van der Waals, which means more energy required to overcome it, right? More energy required to overcome it. Now we have some conversions going on over here. Hexane can be converted into compound E and F at high temperatures and pressure. Shows the reaction scheme involving hexane, E and F. So we have hexane over here. We're converting into this ring structure kind of thing. And then we're converting into this ring kind of structure thing. And identify suitable reagent for reaction 3. So what's reaction 3? Reaction 3 is basically converting this double bonded thing, there is 3 double bonds, converting this thing into a thing that has all single bonds. So what are you doing? You're just breaking the double bonds, and for that you're not adding any chlorine or any other thing. Otherwise you would see some chlorine or water or some kind of thing over here, but you cannot see it over here. That means you're just adding hydrogen to it. So what you're doing, you're doing hydrogenation of your alkenes. That means you're adding nickel catalyst, right, to it. So it's hydrogen. The suitable reagent is going to be hydrogen gas with nickel catalyst. You can tell hydrogen gas, but you don't need nickel. Yeah, you know it. For alkenes addition reaction, you need nickel. So with nickel catalyst with Ni as a catalyst. Okay, use the data in figure 3.2 to calculate the enthalpy change of reaction 2 delta H2. So we have to calculate the enthalpy change for this reaction, right? The reaction 2. For that, we got to figure out one thing, that what's the enthalpy change for reaction 3, because we have the enthalpy change for reaction 1, but not for 3. So how do we figure out for 3? We have the delta H of formation of this thing and this thing. So what we're gonna do, I always do it conceptually. So I'm gonna first draw this ring, right? And then I'm gonna make the double bonds, which are here, here, and here, being converted, right, into this ring, right? So now over here, the delta H formation of this thing is negative positive 48, and for this thing it's negative 156. So what's going to be the delta H or over here? It's going to be of two roots. So one is this one and the one is this one, right? For the first root, it's going to be delta H node R equals plus 48. Delta H naught R plus 48 equals to negative 156. So delta H naught R equals to negative 156, negative 48. So delta H naught R equals to negative 156, negative 48. Negative 156, negative 48 gives me 204. So it's a negative 204. I know for this reaction it's now a negative 204. Now I know there are two pathways for reaction 2. What are those two pathways? Simple, easy. The first path is going from here to here directly, and the second path is going from here to here. Now I'm going to equate these two paths, right? So for the first path, I have this value and this value. So I'm going to tell the examiner that plus 215 negative 204 equals to delta H naught reaction 2. So 204, negative 204 plus 215 plus 215, and this gives me 11, a positive 11 kilojoules per mole. So it's gonna be 11, a positive 11. Write an equation for the complete combustion of hexane. So hexane is C6H14 plus oxygen, gonna give me carbon dioxide and water. And how do I balance it? I put a 6 here, a 7 here, and then I check out my oxygens. 12 oxygens plus 7 oxygens, 13, 14, 15, 16, 17, 12, 13, 14, 15, 16, 17, 18, 19. So it's 19. And how do I get a 19 over here? I would have to put like a, if I put a 9 over here, I have to put 9.5, right? I have to put a 9.5 over here. Now I have to multiply the entire equation by 2 because I don't need a 0.5 here. I put the 2 over here. 9.5 times 2 is going to give me a 19, right? 6 times 2 is going to give me a 12, and 7 times 2 is going to give me a 14. So a 12 here, a 14 here, right? Okay. Figure 4.1 shows how propane can be converted into propanoic acid. Propane converted into a halogenoalkane, converted into an alcohol, converted into propanoic acid. A series of reactions are happening. Reaction 1 in figure 4.1 takes place in the presence of sunlight. So this reaction is going to take place in the presence of sunlight. Right, the reaction takes place via initiation, propagation, and termination step. Name the mechanism shown by reaction 1. So the mechanism is free radical substitution. Why? Because you can see it for yourself. Over here you have an alkane, right? An alkane being converted into a halogenoalkane. So alkane to halogenoalkane, you use free radical substitution. So that's free radical substitution. Complete the mechanism for reaction 1. Construct equations to describe the steps of the mechanism. So that's initiation. We have to write 2 equations for propagation and 1 equation for termination. For termination, you can see that we're making this thing. So for propagation, what are we going to do? We're going to take our propane molecule, which is CH3, CH2, and CH3, right? That's propane. And we're going to make it react with the chlorine free radical. And when we're going to make it react with the chlorine free radical, what are we going to form? We're going to form HCl, right? And a hydrogen is going to be plugged out from the first carbon, you can say. So you're going to form CH3, CH2, and then a CH2 radical, right? In the second reaction, we're going to make this CH2 radical react with the chlorine molecule. So we're going to take a CH3, CH2, and CH2 radical, make it react with the chlorine molecule, and now what are we going to form? When we make a free radical react with a molecule, we form a chlorine radical plus a halogenoalkane, which is going to be CH3, CH2, and CH2Cl. Next things next. Now we have to do the termination. So in termination, we're going to make 2 free radicals react together. And what are the 2 free radicals going to be? CH2 dot plus Cl dot, and then we're going to form this. Simple, easy, I don't think needs any explanation. Free radical substitution, if you got to give A levels, AS level this year, it should be on your fingertips. Reaction 1 is initiated by the bond fission of chlorine. State the type of bond fission shown in the initiation step. Okay, so what kind of bond fission is happening in the initiation step is that you have a chlorine bond, and what happens is, because you not only got to learn things, what you got to learn is that this chlorine and this chlorine, they have equal electronegativity values, and when they have equal electronegativity values, they're both going to pull the electrons with equal intensity towards each other. So that's why there's going to be a homolytic fission, right? We're not going to have heterolytic, we're going to have a homolytic fission. Homolytic fission means that one electron is going to go with one chlorine and the other electron is going to go with the other chlorine, right? Compound Q is a byproduct of reaction 1. This compound is a byproduct of reaction 1. Okay, so what is reaction 1? Reaction 1 takes place in the presence of sunlight. You have your propane, you add chlorine, free radical substitution occurs. You form 1 chloropropane plus HCl, and the byproduct also includes 2 dichloropropane, right? So name Q 1 2 1 and 2. We have 2 chlorines on first, so it's a dichloro, right? We have 2 chlorines. The first chlorine is on carbon 1, the second chlorine is on carbon 2, carbon 1, carbon 2, dichloro, and then because we have a 3 carbon chain, so we have propane. So that is 1 2 dichloropropane, right? 1 2 dichloropropane. The molecular formula of Q is this. Identify the types of structural isomerism and stereoisomerism that a molecule with a molecular formula this can show type of structural isomerism. Okay, first is that we have 3 types of structural isomerism, right? One type of structural isomerism is chain, right? We're talking about a structure. The other type, 1, 2, is functional group, right? Functional group. And number 3 is position. Now you got to know one thing. When you have 3 carbons arranged in a row, you cannot make a chain. You cannot make a chain with 3 carbons. Take it, write it somewhere, you cannot make a chain. Why? Because if you have 3 carbons and you put 1 carbon down, it again becomes a linear line like this, right? If you have 3 carbons and you put 1 carbon down here, it again becomes linear. You cannot form a chain with 3 carbons. So it cannot give you chain isomerism. Functional group isomerism means that there's a different functional group. With 2 chlorine atoms, you cannot have any functional group except for halogen or alkane. You cannot change the functional group too. The only thing you can do is change the position of the functional group. You can place this chlorine on one atom, then on another carbon, and that's the only thing you can do. So the only isomerism that's going to come over here is going to be your position isomerism. So the type of structural isomerism is going to be position isomerism. Okay, type of stereoisomerism. Look, this is the type of molecule you're dealing with, which is C3, Cl over here, Cl over here. You can place it anywhere, by the way, if you only have the structure, like the formula right here. If you only have the molecular formula. Now look at this. There are 2 types of stereoisomerism, right? There are 2 types. The first type comes out to be your cis trans, which is known as your geometric, and the second type comes out to be your optical, which has a chiral carbon. Now you got to look for one thing. What's that one thing? Look at cis trans. Cis trans only comes when you have a carbon-carbon double bond, because you got to have restricted rotation around the double bond. So we don't have any double bond in this molecule cross. The only isomerism possible here is optical, and for optical you need a chiral carbon. Look at this carbon over here. It has this CH3 bonded over here, a chlorine on top, a hydrogen on bottom, and a CCl-CH2 over here. So there are 4 different groups. This, and this are 4 different groups, right? So type of stereoisomerism over here is going to be optical isomerism, right? State the reagent and the solvent required for reaction 2. What's happening in reaction 2? So we have this thing over here, and then we're converting it into an alcohol, guys. Alcohol. I'm very hyperactive. I have ADHD. Okay, halogen alkane to alcohol, right? So what do we do when we have a halogen or alkane and we have to convert it into an alcohol? We add NaOH, and the condition for that NaOH should be aqueous, right? It should be in water. Because if we have NaOH, that's ethanolic, right? Then we're going to form, what are we going to form? Then we're going to form that thing, what do you call that thing? That's an alkene. Then you form an alkene from a halogen alkene. But if you got to form an alcohol from a halogen alkene, you got to have aqueous NaOH, okay. Reaction 3 take place when this thing is heated under reflux with acidified potassium dichromate. State the color change. We have an alcohol, we have a primary alcohol, we're heating it, so we're going to form under reflux, right? Not under distillation. So we're going to form an alcohol, right? We're going to form an acid, right? Yeah, if we heat it under distillation, we're going to form an aldehyde. Under reflux, we're going to form an acid, propanoic acid. So state the color change. We're oxidizing a, what is this thing called? We're oxidizing an alcohol. The color change is going to be from orange to green, right? No problem. Acidified potassium dichromate. Dichromate is orange in color and it's going to turn green when it's going to be acidified. Construct an equation, right? Construct an equation to represent reaction 3. Construct an equation to represent reaction 3. Okay, so we got to construct an equation to represent this reaction right here. You know why do they ask this? Because they know that you're not going to form water. Water is also going to be eliminated over here. I'm going to show you how, why, everything. What happens is that you have an alcohol, right? Let's take this alcohol, whatever this thing is. Okay? Propanol, right? Propan-1-ol. Because we're in A levels now, we don't say propanol, we say propan-1-ol, right? And you add oxidizing agent to it. Add oxidizing agent to it. Oxygen is being coming over here. Now what's going to happen is that, honestly, the first things first, you have an H over here as well, right? In H over here. This hydrogen is going to come off. This hydrogen is going to come off. Okay, what things we're taking off. And this oxygen is going to go over here, make a double bond. And one oxygen, we're going to use two oxygens, is going to come here, right? It's two hydrogens, one oxygen. This bond gets vanished away, like here, right? We form propanoic acid. So with propanoic acid, which is the same thing, we form one water molecule as well. So the only thing you have to write is two oxygens and one water, right? That's the only thing. Okay, CH3, CH2COH, which is propanoic acid, reacts with an unsaturated alcohol. Okay, so to form an ester, right? That's a acid, that's an alcohol. We're going to form an ester. State the type of reaction that forms S. State the type of reaction. Condensation reaction. Esterification is an example of condensation reaction. Why condensation? Condensation reactions are reactions in which you have the removal of water, right? So what do you do in esterification? You have an acid, you have an alcohol, you form an ester plus water. So whenever you are forming water, you remove water. That means it's a condensation reaction. The infrared spectrum of S is shown in figure 4.2. That's the spectrum. You can see some peaks over here like this, whatever this is, right? Okay. 3 absorptions in the infrared spectrum in figure 4.2 confirm that S is an ester and is unsaturated. Unsaturated means it has a carbon-carbon double bond, right? Write 1, 2, or 3 in figure 4.2. We have to write 1, 2, or 3 against each of these 3 absorptions. Complete table 4.1 to show which bond is responsible for each absorption that you've identified in figure 4.2. Okay, so we have this table over here, right? And we have this thing over here. We have to write 1, 2, 3 and tell that which absorption is responsible for which. So the first thing that I think I'm going to write in the table is, like, I know it's an ester, so I am going to go with this ester thing. I know it's unsaturated as they told, right? So unsaturation means carbon-carbon double bond, right? And the third thing that they told was, it's unsaturated ester, right? So it's, since we have to prove there is a infrared spectrum confirm S is an ester, ester is going to have, right? Ester is going to have this group, right? So we also need the CO. So the CO, where is the CO? Look, we have it here, right? For our ester, we're gonna mark it like between 1710 and 1750. So first bond we write C C double bond O, where is 1750, 1500, 1600, 1700. This is 1. So I'm going to mark this thing 1. And the second bond is C double bond C. Where should I mark it? C double bond C. 1500 to 1680. Where is 1500? This thing is going to be 2. I can see it. And the third thing that I'm looking for is 1040 to 1300, right? 1040 to 1300. 1040 to 1300, 100, 200, 300, this thing. So this is going to be marked as my third thing, right? I think that's the only thing I have to do. Okay. The mass spectrum of S shows the following peaks. This and this. Use table 4.3 to calculate the number of carbon atoms in S. Okay. So what we're going to do, m plus 1, which is 0.31, divided by m, which is 4.7, multiplied by 100, right? Divided by 1.1. And this is going to give me how many carbon atoms? 6 carbon atoms. That means we have propanol, propenol, right? Propenol, hydroxypropene, something like that kind of thing, because we have unsaturation as well as that thing, whatever that thing is. What do you call that thing? Alcohol group, right? So done with today's paper.